And we're back. So, chemistry. It's often called the central science. There's actually a chemistry textbook that's titled that, the central science. The reason for this is that chemistry is very closely related to essentially every other science that you'll ever come across. Chemistry is connected to it in one way or another. This is not quite as true for other sciences, although there are other ones that are definitely closely connected to everything else as well. Physics, for example, is very closely related to lots of other fields, but physics is much more on the details side, I guess you could say, the tinier side. It's more of an abstract science than chemistry is, although there is quite, don't get me wrong, there's quite a bit of physics that is working with real life things, but then there's quite a bit of physics like particle physics and things like that where it is more abstract, it's more thinking about things and actually interacting with them. And chemistry is kind of a happy middle where it's very much a hard science. It's close to physics and to other chemical engineering and things like that, but it's also closer to some of the softer sciences like biology. And so because it's kind of that happy middle, it's kind of right in the middle, this is the central science. It's closely connected to lots and lots of other types of science. Moving on here, let's talk about the scientific method. So this is something that you were probably taught, maybe even in elementary school. It's being taught earlier and earlier, which is a good thing. But at the very least, you should have learned about the scientific method in high school. This is a method for thinking, is all the scientific method is. It's a way of investigating the world through a set process. This process of thinking about the world and investigating the world always starts with an observation that sparks a hypothesis. So we're always going to see something, we're going to observe something, and that is going to make us think, I wonder if that thing that I just observed happened because of this. We'll then take that hypothesis and test it to see if it's correct. We'll design an experiment to see if that hypothesis is correct. And so it's going to look something like this. We'll have an observation. We'll form a hypothesis to explain the observation. We'll then perform an experiment to see if our hypothesis is correct, and then that experiment will give us some sort of a conclusion, and that conclusion will either be telling us that our hypothesis is inconsistent with the results that we got, or that it is consistent. Now, if we get a consistent, the hypothesis is supported by the evidence conclusion here, that does not mean, all right, science is done. We have proved our hypothesis. No. No, no, no. Science is never done. Ever. So if we get a result that supports a hypothesis, the least we should do is reproduce the experiment. So the very least we should do is do that experiment 2 or 3 more times just to make sure we get the same result each time. There's a very, very common saying, I believe it's something like insanity is doing the same thing multiple times and expecting a different result. In science, we do the same thing multiple times, and we expect to get the same result. But in reality, quite often we don't. And that is not because that the universe has variable laws, and you do an experiment one day, and it gives you one result, and then just because it's a different day, all of a sudden it gives you a different result. No, it's because people doing experiments are flawed. The people doing the experiments are flawed. Maybe the equipment that's used is flawed. Maybe the materials that are used is flawed. Mistakes can be made. Mistakes can be created. You want to do the experiment multiple times so that you're sure that the result that you got is correct. That it is, in fact, the true result. I have seen this myself. I was a graduate student at TU, and I did lots and lots of experimenting, and there would be times where it would be so incredibly frustrating because I would do an experiment multiple times, and I would get a different result every time. And I just had a devil of a time trying to figure out why I was getting different results. And eventually I would usually get to the point where I could refine my process to where I wouldn't get necessarily exactly the same results every time, but it would be very, very similar. It'd be consistent enough that I could get good information. Because that's the most frustrating thing, is if you do the experiment multiple times, you get different results and you have no idea why. You don't, there's, not only did you waste all the time doing the experiment, you didn't even get, you didn't get any data as a result. On the other hand, if you run your experiment and the result that you get says that your hypothesis is inconsistent, that does not mean that you just chuck the whole hypothesis out the window. You don't just say, oh, well, moving on. What that means is you're going to revise it, because maybe that hypothesis is not completely incorrect. Maybe it's just partially incorrect. Maybe one of your assumptions that you had built into your hypothesis is incorrect. You need to change a few things here and there. So you make some revisions, and you create a new experiment, and you just do the process over again. And this process of doing an experiment and getting a result and finding the either getting a correct or incorrect, so to speak, result from the experiment, and you just go through this process over and over again. And eventually, and this is the one part of the table here that I'm not terribly satisfied with, it says that eventually you can form a theory. That's not actually true. A single hypothesis would never be converted into a theory, or at least very, very, very rarely would it ever be directly converted into a theory. It would usually support a theory, but it wouldn't create a theory in and of itself. But even at that point, if you've done a whole bunch of experimenting and you get to the point where you say this has been vetted enough, it's been tested enough, that we could consider it a scientific theory, you're still going to do further experimentation. Like I said, science is never done. There's no end to science. There's never going to be a point where people say, all right, everything has been discovered. We know everything. That is never going to happen. There was some person back in the 1800s in the United States, and I do not remember his name, but there was some person back in the 1800s, back when people were riding around on horse and buggy and going to the bathroom in the backyard in an outhouse. There was some guy that said there is nothing new to be discovered. Everything that will ever be discovered has been discovered. And this was back in the 1800s. He was very wrong. That guy was an idiot, whoever he was. There's still many, many more things to be discovered. Science will never end. This is the flowchart from your book. It's supposed to be the same overall idea as the previous one, but I don't like it as much. But there is one thing on here that I do want to point out, and that is that we have this new category here of law. So on the previous flowchart, we only had hypothesis and theory, but in reality, there are actually three tiers, so to speak, of ideas in the scientific method. Hypotheses, we'll just say a hypothesis. We'll go with that. A hypothesis is based on a few observations and is meant to explain those observations. So it's very specific, it's limited in its scope. So an example of that would be that combustion requires oxygen. That is very much more specific than it could be. It's slightly broad because it is covering all combustion reactions, but it is only covering combustion reactions, and there are lots of other kinds of reactions. A law is a statement that synthesizes many past observations and predicts future ones. So an example of this would be mass is conserved in chemical reactions. So it's taking lots of different hypotheses and saying, okay, based on all these different observations that we've done, all these different hypotheses that have been put forward. We can have some more broad statement about the nature of the universe, and then the third and most broad definition is the theory. So this is broader, deeper explanation for many observations and laws. This is a more elementary, more basic, if you want to think of it that way, type of way of thinking about the universe. So the atomic theory is an example of this. And so the atomic theory is that all matter is made up of small particles called atoms. So this covers everything in the entire universe can be described using this theory. It is a foundational idea of science, is a scientific theory. So with that in mind, which statement best explains the difference between a law and a theory? Is it A, a law is truth, a theory is mere speculation? B, a law summarizes a series of related observations, a theory gives the underlying reasons for them? Or C, a theory describes what nature does, a law describes why nature does it? So go ahead and pause the video for just a second, and I want you to think about those three possibilities and think about which one you think is the correct answer for the description of the difference between a law and a theory. So pause the video now. Alright, I hope you paused the video there and give it a minute to think about it. So the correct answer here is B. A law summarizes a series of related observations. A theory gives the underlying reasons for them. This is very closely tied to the definitions that we had on the previous slide here. Now, if you answered C, that sounds correct, except, and it could maybe be correct if they were flipped. So if it said a law describes what nature does and a theory describes why nature does it, that could be correct, although I would still have a bit of an issue with the statement that a law describes what nature does. I'm not super happy about that, but I could see how it could be taken to be correct. But having them flipped like this, where the theory is talking about what things are doing and the law is describing the underlying reason why it happens, that is definitely backwards. It should be flipped the other way. And then that first one there is not correct because when we're talking about science, where we don't really talk about laws being truth and the theory is mere speculation. First of all, the theory, a scientific theory would actually have more proof behind it, would have more thought behind it than a law would, and so it wouldn't be mere speculation. But even in science, you know, there's, I might every once in a while use the term truth, but when it comes to science, we hesitate to use the word truth in science, just because that's more of a philosophical term. So, at least me, I personally hesitate to use the term. Alright, so in the next video here, we will talk about classifying matter. So we will get into that next time, and I'll see you.